Hello everyone, my name is Bhavya Muthaneni and I am pleased to present our project title Ensemble Approach Towards Heuristic Features on Deep Learning Algorithms for Coronary Artery Disease Prediction and Drug Recommendation. This work was collaboratively done by Lakshmi Kiranmai, Venkat Sai Jashwant, Raveen and myself. We would like to express our sincere gratitude to our Professor Dr. Sangsu for guiding us throughout this research. Next slide. This research combines autoencoders and light GBM in three phases to enhance CAD prediction, achieving 99% accuracy without overfitting. The approach scales for baseline modeling to learning and multi-label classification for robust large-scale applicability. Can you change the slide? Yes. Coronary artery disease is a major cardiovascular issue caused by the narrowing or blockage of coronary arteries. It often leads to severe complications like heart attack. Importance of early detection. Identifying and predicting CAD early can save lives. Existing models face challenges like low accuracy, data complexity, and lack of integrity. Our project tackles these gaps by combining autoencoder with Ensemble learning to enhance CAD prediction and drug recommendation. Next slide. Current research landscapes are privacy preserving methods, Ensemble machine learning, hybrid approach, and stacking models. Next slide. Deep learnings in CAD technologies like CT angiography enables automated feature extractions and integrations of multimodal data combines data types enhance detection with Parker using transfer learning and Yan focusing on phonocardiograms. Next slide. Challenges in current model, high dimensionality, uh, complex model data sets, challenging tradition models, class imbalance, unequal diseases, classes disturbing accuracy, and privacy concerns. Patient data security remains a critical issue. Lack of integrity, limited uses of advanced features, extended and assemble learning in CAD. Next one. Objectives. Our goal is to create a robust framework using Ensemble autoencoders to enhance CAD prediction accuracy. Key features are uh, feature extraction, Ensemble learning, and addressing classes imbalance. Next slide. Benefits of this project is improving prediction accuracy and adaptability to real world data sets, better handling of complex imbalanced data, and enhancing patients outcomes. Now Ravin will take over and explains the related work in detail.
Thank you so much, Bhavya. So in this section, we will review key advancements in machine learning and deep learning for CAD prediction and drug recommendation. We will explore existing studies in 5 key areas: privacy preserving techniques, ensemble methods, feature balancing, deep learning innovations, and advanced imaging approaches. So in privacy preserving techniques in healthcare, it is proposed cloud-based hyperplane decision-based classifier combines data privacy with diagnostic accuracy and highlights challenges in practical implementation of privacy preserving system. And ensemble and hybrid learning approaches proposed ensemble ML with cardio or ultrasound for CAD prediction and ensemble learning in risk management for CAD. Next slide. Feature reduction and balancing techniques proposed feature reduction for illness risk prediction, stacking models with balancing strategies for heart disease, stacking based approach for CAD diagnosis, deep learning innovations in cardiovascular diagnosis. It is proposed deep learning for CAD diagnosis and lesion categorization, ensemble transfer learning with phonocardiogram data, multi-scale attention convolutional networks for phonocardiogram data. Next slide, please. Advanced imaging and segmentation techniques propose CMAR pipeline for coronary artery alignment, efficient segmentation of coronary arteries, accurate segmentation and diameter measurement, comprehensive approaches and future direction proposed 2D CNN for detecting inferior myocardial infarction, hybrid deep learning for cardiac condition forecasting, pulmonary circulation model for artery stenosis detection. Next slide. Drug repositioning and prediction techniques proposed NetPro for drug repositioning, multi-kernel DL for drug disease prediction, low-rank matrix factorization for association detection, learning methodologies and computational approaches proposed hierarchical contrastive learning for drug disease associations, collaborative metric learning for drug repositioning, graph regularized matrix completion for disease prediction. Next slide. And the challenges in previous one. This is the one. Innovations in Ensemble learning and disease detection, nested Ensemble clinical decision support system, autoencoder based dimensionality reduction for ECG data, beta variational autoencoders for health abnormality detection. Next slide. And challenges in CAD detection. CAD often progresses silently without clear symptoms. Traditional diagnostic methods such as imaging and angiograms are costly, invasive, and time consuming. Role of machine learning and deep learning. ML and DL analyze diverse patient data, including demographics, medical history, and clinical parameters. They identify complex patterns and subtle risk factors contributing to CAD. Advantages of DL and ML models: improved diagnostic accuracy and early detection, support for personalized treatment plans and timely interventions, enhanced efficiency and accessibility for broader population healthcare, impact on healthcare, proactive, cost-effective solutions for CAD prevention and management. Next slide. Proposed approach importance are dimensionality reduction, robust classification, real-time prediction, and advantage over traditional methods. Next one. Now I would like just one to take over to talk about methodology section. Thank you.
Yeah, I'm sorry. Thank you, Ravin and Bhavya, for the introduction and related work. And coming to methodology, coronary artery disease and stroke are significant cardiovascular conditions with shared, just a second. Yeah, with shared risk factors such as hypertension, high cholesterol, smoking, and sedentary lifestyle. And CAD occurs when plaque buildup narrows coronary arteries, restricting blood flow to the heart, potentially causing heart attacks. And in here we are using a couple of classification approach to detect coronary artery diseases. Whereas in these approaches, we have data utilization approach, where we are compressing and decompressing the data for training and testing purposes. And we are using binary versus multi-level classification for comparing with multiple methods in machine learning approaches. And can we move to the next slide, Karan? Yeah, here is the block diagram of our coronary artery disease prediction, and which consists of two layers. Yeah, as shown in the figure, it begins with data collection and pre-processing the data set and we are collecting the data from the data set from data.gov website, which contains US mortality data related to coronary artery diseases and stroke. The first step involves in loading the data, cleaning it by handling missing values, and preparing it for model training. This pre-processing phase is critical for ensuring the quality and consistency of the data. And the data pre-processing might also involve splitting the data into training and testing sets, and potentially augmenting the dataset to balance any class imbalances, which is common in healthcare data sets. And the system then performs feature extraction using AUTOENCODER, which is a deep learning based method for reducing the dimensionality of the data set. And the AUTOENCODER is The autoencoder is a neural network that consists of two main parts, the encoder and the decoder. Whereas the encoder is used for the compressing the data and decoder is used for decompressing the compressed data. And we also have one more important part, which is latent space. It captures the most critical features and then helps it oh, I'm sorry, and then helps it to decompress original data without much loss in the data. And then the data from the compressed data from the latent space is then transferred to training and testing, which is where we are using multiple machine learning models at a time, such as decision trees, random forest, support vector machines, and neural networks. All these machines are trained at parallelly, not one at a time, and then based on the results from the metrics from these methods, we are predicting the disease prediction using the voting system based on the accuracy and F1 score and other metrics. And can you move to the next slide, Karan? Yeah. Next slide, please. I already done with that. Can you move to formulations? Yeah. Here are the formulas that we are using in for autoencoder and ensembling. The formulas that we are using in autoencoder is encoder, decoder, and reconstruction loss. And for here the encoder formula, where Z is the compressed data and X is the input data which we are compressing, and F is the function that we are using for compressing. And here W stands for weighted data for weighted, and B is the biased data where X is the input, and sigma is the sigmoid function. Similarly, the decoder is using the same step where X dash is the recompressed data from which we are recompressing from the compressed data, and G is the function for recompressing the compressed data. And here we are reducing the loss by using mean squared error, where L is the loss of data and N is the number of data we are inserting. Here we are using three phases, in which the first phase we consist of 32K samples, and the second one consists of 80K samples, and the third phase consists of 160. N is similar in each phase. N varies, and Xi is the number the data at the number at the specific, and X dash is the recompressed data. And let's just a second. Yeah, and in ensemble forms we are using individual modules and voting mechanisms and weighted voting for calculating for the predictions. Can you move to the next slide, Kiran? Oh, I think you can start with the implementation. That's it for the methodology.
Thank you, Jashwant. I'm going to explain about the implementation and results. For this experimental setup, we need the hardware, Dell Inspiron 15R laptop, and multi-core processor with 8 GB RAM and integrated GPU. And we'll use the Python libraries like TensorFlow and scikit-learn, and the develop environment will be using the Jupyter Notebook for this. And optimizing strategies is running experiments in batches, and we'll use the GPU to accelerate autoencoder training, and the several ensemble models like decision trees, random forests, and SVMs and neural networks will be utilized. And coming to the implementation workflow, here the steps are like data pre-processing, feature extraction with autoencoder, model training with ensemble learning, and evaluation and visualization, where data pre-processing is used to handle the missing values, and feature extraction with autoencoder will be used for the encoder compresses input into a latent space for dimensionality reduction. And model training combines multiple models to enhance the accuracy and robustness. And coming to the evaluation visualization, the performance metrics like accuracy, precision, recall, and F1 score will be evaluated. Coming to the phase 1, as Jashwant said, there will be 3 phases, like we'll be considering 32K samples, 60K samples, and 120K samples. Coming to the phase 1, the main goal is to establish a baseline for model performing using 32K samples. And the steps are like data pre-processing for cleaning data set, removing noise and handling missing data, and normalize numerical features and encode categorical variables. Coming to the model selection, we are using the light GBM for its efficiency with smaller data sets, and we'll be evaluating accuracy, log loss, precision, F1 score, and we'll be using the employing k-fold cross-validation to avoid overfitting, and tuning adjustment hyperparameters for improved accuracy. Coming to the dataset overview, the dataset name is CAD dataset, and we are taking this dataset from data.gov, which is a public health database, and its main purpose is to analyze and track the prevalence and distribution of coronary artery disease. And firstly, pre-processing of the CAD dataset, its objective is to enhance data quality for descriptive and predictive analytics using robust pre-processing techniques. And its steps in pre-processing, as we discussed, will be handling the missing data, encoding categorical values, scaling and normalization, and feature significance. And the application in machine learning models, it's heuristic based techniques, weight features like priority area 1 and class based on importance identified through feature importance methods. And as we discussed, we'll be using the k-fold cross validation, so that it can be done in batches for robust evaluation, reducing overfitting and enhancing generalization, and incorporating differential equations, model dynamic relationships such as healthcare access versus CAD rates with differential equations. And coming to the integration with Ensemble model, we'll be utilizing Ensemble with heuristic model, LGBM, light GBM, nothing but light gradient boosting machine, and applying heuristics for domain-informed feature weighing. And it is like leverage pre-processing to boost accuracy during the k-fold cross-validation, and it delivers adaptive real-world insights into CAD prevalence. Feature extraction with heuristics. The mathematical representation for this will be adjusted feature weight equal to feature value plus W1 plus into domain adjusted factor. And coming to the implementation in Ensemble model, heuristic adjustments are integrated into Ensemble with heuristic model. K-fold cross-validation ensures the model generalizes well while incorporating domain knowledge. And this is the ROC curve. In this, the train and test accuracy both are 100%, which are indicating the perfect prediction performance. And for training and testing F1 score, both shows 1.1, nothing but 100%, showing balanced precision and recall. And for training and test confusion matrix, there are no false positives or false negatives, which are demonstrating the perfect classification. And log loss is extremely low. It's very, very low. As we see here, it's 0.00022, which indicates the confident predictions. And coming to recall and AUC, it's both like 1.0 for both, meaning all positive cases for identified currently, and for AUC, it indicates perfect class discrimination. And coming to this, this indicates the accuracy and loss plots, training and testing cases when we are doing for 30K samples. Here we'll be combining both like AUTOENCODER and light GBM, nothing but the ensembler approaches. This is what it shows if we consider the 30K samples out of the data set. And coming to the phase 2, we'll be considering 60K samples, and the adjustment for scale, it is advanced feature engineering, including interaction terms and polynomial transformations, and the distributed learning techniques in light GBM for faster training on larger data sets. And evaluation techniques that it increases the cross-validation folds, which is meant to ensure generalization, and incorporate additional metrics like precision, recall, ROC, AUC curves, for mainly the detailed analysis. And autoencoder design and analysis objective is to analyze autoencoder performance on 60K samples. And the key components for this will be autoencoder design using convolutional layers, feature engineering, and integration of autoencoder with LGBM. Coming to the autoencoder design using class, there will be model overview and training phase. In model overview combines con 1D and max pooling 1D. And in the training phase, the data pre-processing, like missing values and normalization using standard scalars, and train, test, split, and feature adjustment for con 1D compatibility. And here we'll be using the hybrid model, which is nothing but autoencoder plus light GBM, where the architecture consists of like autoencoder, dense classifier, and light GBM. Autoencoder is nothing but learns latent representations of the input data, and dense classifier is a multi-layer which is fully connected with the network for binary classifications, and light GBM is used for feature ranking. And coming to the pipeline, feature selection, like nothing but light GBM ranks features, autoencoder encodes the most important features, and dense classifier performs the classification task. This is the accuracy and loss plots for training and accuracy, like training and validation loss for 60K samples. And we can see like epochs, and here is the details like where the accuracy from 75% to 95%. And the process autoencoder encodes features, LGB learns from encoded features. Same like in the mid training, it varies from 98 to 99%. And from the late epochs, it varies from like 98.64% accuracy. Coming to the phase 3, we'll be using greater than 120K samples. We use literally like 160K samples or so to check the difference between the evaluation matrices. The main focus is for like large scale data set management and computational efficiency. And we'll use the batch processing, and we'll be stratifying the samples, which ensures balanced data set splits for training, testing, and validation. And like advanced hyperparameter optimizations, like these are the tuning methods like kind of Bayesian search and grid search, fine-tune parameters like max depth, learning rate, and num leaves. And as and coming to the primary goal of this, demonstrate data pre-processing techniques and advanced classification using autoencoder based models. And it focus mainly on areas like handling missing data, multiple label, and performance. Data preprocessor class like key features like same like handling missing values and replacing the missing values and encoding categorical variables, and creates a streamlined pipeline. How will like as we discussed, how will handle the missing values? There will be one differential equation. It is this like dx by dt equal to a into x plus b, where a will be the matrix defining relationships, b will be the bias vector adjusting the equation, and it ensures robust data imputation influenced by existing patterns. And this will be the accuracy and loss plots for training and testing cases with hybrid design, light GBM, and autoencoder using multi-label. Here we'll be using the 120K samples, but multi-label. Previously, we used 30K samples and 60K samples for binary. So yeah, this is the output, and this is the output for like evaluation metrics, which we're using the multi-label. Here, as we can see, we got the accuracy like 0.99%, and this is the highest accuracy we got. Coming to the conclusion, the autoencoder based models in this study show exceptional performance in cardiovascular disease classification, and there will be a substantial potential to improve the approach by integrating some kind of advanced deep learning methods, heuristic methods, and sophisticated machine learning methods. And enhancements such as ensemble methods, real-time deployment, multitask learning, which can make the solution more robust for diverse healthcare applications. And additionally, focusing on this model will utilize new AI advancements, will ensure the model's practical value in like future supporting healthcare professionals with accurate and with timely decision making. And I want to quickly explain the code. Just give me a second. Yeah. As I told, we'll be working on the 30K samples and all. So this is the code for the 30K samples, where we'll be taking the 30K samples and performing the data pre-processing, encoding labels, and pre-processing the data. And we'll be getting like when we'll be performing the curve k-fold validation as well. And we'll be getting this is like before combining both methods. And as we discussed, this is the output like where we combine both the light GBM and like ensemble methods and autoencoder methods. And this is the accuracy we got for 30K samples. And same for 60K as well. We'll be like performing all the steps like data pre-processing, encoding labels, and everything. And we'll be getting this I'm sorry, yeah, we'll be getting this output once we combine both the algorithms. Same for 120K, and as I mentioned, we'll be using the multi-label as well. And like for 30K, 60K, we'll be using the binary, and for this, we'll be using the multi-label. We just want to check which gives more accuracy and all. But as we combine the both methods, everything for everything, we got like around 97 to 100 accuracy. And we compared the existing algorithms as well. And yeah, finally, we got the accuracy what we expected from the by the combination of both algorithms. And this will be the conclusion for that. And these are the references. We have taken 64 references, and we included all of them. Yeah, these are the references that we included. And thanks for giving this opportunity.
Thank you.